All right, how's it going, everybody? Welcome to week 6. We are here still in the middle of our chapter 7, looking at more of our integration techniques here. Today, we're going to get a pretty nice technique. This is one that I've always appreciated. Partial fraction decomposition is one of those things that always takes some work, but the work itself is never really that bad. As with lots of things in this class, it's a lot more about staying organized than it is about um, thinking difficult thoughts. And so this is, as I say here, as long as you enjoy going on small algebra adventures, I think that you're going to find this to be a very satisfying section right here. This is really just saying, what's the smartest algebra that we can do to make our integration as easy as possible? So the big thing about 7.4 is there is no major calculus idea that's happening in this section. The major idea here is recognize that you're better at algebra than you think that you are, and that you should be able to do some heavy algebra lifting in order to make sure that you don't have to work too hard when it comes to the calculus ideas. The big idea of this section is that simple rational functions are very easy to integrate, and that complicated rational functions are very difficult to integrate directly anyway. I'm leaving just blank for a little example right here. We know some basic things like the integral of 1 over x dx. Well, that's just the natural log of x, right? That's really easy. And even if we get some very slightly more complicated things here, I can still even do things like 1 over 2x plus 5 dx. And I can still pretty easily think of this as maybe I factor out 2. So 1 half integral of 1 over x plus 2.5 dx. And that's going to be leaving us there with 1 half natural log of x plus 2.5 plus c. Right, so pretty simple here. As long as we can get ourselves down to just having a linear factor in the bottom of a fraction, then the integration itself is essentially automatic, right? We know that the integral of 1 over x is the natural log of x, and that's basically as complicated as we want the actual integration to be for this entire section. Our job, this section, is to get out our algebra beating sticks and to beat things into simplified form that are not currently in simplified form. And I can tell you, some of them are going to resist, and that's why we're going to use sticks and not ask nicely, because some of these are going to take a little bit of effort to get into the simplified form. But it should be for all of the problems associated with section 7.4 that the doing of the calculus is not actually any harder than what you see on my page. It's the algebra setup that we're really here to focus on in section 7.4. So let's go ahead and, as we've been doing, we're just going to kind of work through some book examples here today. I figured I should maybe do more organizational things for you in a video, like actually tell you what we're going to do so that you know kind of where you can look ahead, skip ahead, stuff like that for the problems of interest for you. And I'll also tell you here, some of these problems we're going to do exactly as the book said. Other ones I just sort of made up my own problem, and I found a problem in the book that's like very close to what I was doing. So some of these are approximate problems that we're doing from the textbook right here, but they're the same in spirit here. So let's go ahead and start looking at some examples of what we mean by doing some of the algebra of interest here. The first example that we want to look at here is we're looking at a quadratic. All right, so we've got 2 divided by a quadratic, and really these denominators are going to be the most important thing for us to keep an eye on here. The numerators are going to, in a sense, be allowed to do whatever they want. The denominators are the thing that we're really going to have a fight with here today. So you should notice, first things first, is that I don't have directly a super great way to re-express anything in this integral right here. I can't directly do integration because I don't know about my integral of like 1 over x squared type stuff. I can't, doesn't look like I can do like a u sub here. If I were going to do a u sub, it would have to be something like an x squared plus 3x minus 4 for u. But if I were going to do that, then I'd be getting 2x plus 3 dx here, and that doesn't seem to be like something I can work with here. So the point is, this doesn't seem too crazy to me, but this doesn't seem like we can do it directly, and it doesn't seem like we can use any of our simple techniques. This doesn't look like it matches any of the structures that we saw for our trig substitutions, and it doesn't already have trig stuff in it. And finally, integration by parts. Parts is always a toughie with rational functions here because I need to be in control of my numerator and denominator parts for my dv's and my du's. I don't see any direct integration by parts stuff possible here. So what I'm thinking to myself is this literally doesn't look integrable to me. As it stands, I have no way to do this integration. So what that always means to me is let's get out our beating sticks and see if we can make this thing look different so that I can go ahead and perform the integration. So the first thing that I'm identifying is that that looks like a pretty nice and friendly quadratic down there on the bottom. It's annoying to me that it is a quadratic, but at least it looks reasonable to me as far as quadratics go. And wait a minute, did I right away? Uh, Yeah, I think I'm gonna alter that problem ever so slightly right there. Um, right? No, I had that right. What am I doing here? I'm talking myself out of my factoring. See, as promised, this is just an algebra day today, and right now I'm having a factoring fight with myself in my head. How ridiculous is that? That's all that's happening here, though, is we're just doing the algebra here. So I'm thinking if I'm going to factor this guy, now that I'm not crazy like I was for the previous 60 seconds, I think that I can see that I can factor this guy as x plus 4, x minus 1. 4 times negative 1 is negative 4. Positive 4 plus negative 1 is positive 3. So one thing I'm seeing is that it's at least reasonably nice for me to rewrite this as 2 divided by each of these individual 2 factors. What my problem here is, though, is I still don't know what to do with this. That would be super cool for me if I could write this guy instead as something that looked like, something divided by x plus 4 plus something divided by x minus 1. This would be good for me. This is really my desire. My hope is to build something of this structure. So the nice thing about algebra, and hopefully the sense that you're getting about algebra, since I know that now that all of you guys are in Calc 2, you're finally like actually learning algebra, and that will continue to be the case going into DiffyQ, is that the thing that you should learn about algebra is all you need to know is what you want something to look like, and you should be able to mechanically force yourself into that situation. What we currently have is we currently have an expression that looks like this. So this is the beginning of my like major side work right here, by the way. What I really want this expression to look like is some fraction where we just have the simplified linear terms in the denominator instead. This would be ideal for me, is if I could somehow rip this apart, decompose this into its partial fractions. That's our verbiage for this section here. What we don't know is what numerators might be appropriate for us to do the fraction addition to get back to this guy over here. So I'm just going to give it some generic letterings here. And a very typical thing to do in partial fraction decomposition is to use capitalized letters starting from the beginning of the alphabet. This is one of those things where, like, obviously use anything that you want, but like standardizing things is good. It helps you be consistency is the hallmark of a champion. Every time you mix it up on yourself, you are inviting yourself to make a mistake. You should pick one system and stick to it, and the one system that pretty much everybody picks is capital English letters here for these parts here. So the point is, what I don't know is what a smart choice would be for A and B to decompose this fraction into these 2 fractions. But I do have an equation right here. I have a relationship. Now, immediately, I am hoping that the algebra thought that you're thinking to yourself is, but Tony, we have 2 unknowns and only 1 equation. That should be a thing of concern to you right now. I'm hoping that you see that, but I'm also going to tell you that problem will get fixed right here. So let's just go ahead and see what algebra we might do to solve for these guys. If I'm going to try and deal with this equation to try and get useful information about what A and B might be, the first thing that I recognize is that I hate doing math with fractions, so I want to get rid of them. What I would like to do here for my first step always is to clear fractions. And so the first thing I'm going to do is I'm going to multiply this entire expression by x plus 4 times x minus 1. Entire thing, and this is my bad math notation, but I'm multiplying this entire equation by this expression here. So you should notice what we should have left over is just a 2 on the left. On the right, with the A grouping here, the x plus 4 that we multiplied canceled with the x plus 4 in the denominator, but the x minus 1 survived to be part of the A grouping. So I do get an A times x minus 1. Similarly, in the B grouping over here, the x minus 1 that we're multiplying by cancels, but the x plus 4 survives in the B grouping. So we do get a plus b times x plus 4. The thing that I'm noticing now is that we have some constants in our equation and some x stuff in our equation. And here's the important part. I'm going to go ahead and expand real quick here. Ax minus a plus bx plus 4b. And here's the thing that I'm thinking to myself. I don't know what choice I want to make for a and x for this to all work out, but the thing that I do know is that on the right-hand side, I sort of seem like I have some x components, but on the left, I have no x components. So I think a smarter way for me to write this is 0 x's plus 2 equals, and here I'm going to now group together my x terms. So there's some x stuff and there's some x stuff. It looks like I really have a plus b is how much x stuff that I have. Very similarly, how much constant stuff do I have? Well, I have negative a plus 4b is my overall constant term. You should notice that what I'm trying to do right now is do some grouping here. You should notice that I am trying to group up my x stuff with my x stuff. And I am trying to group up my constant stuff with my constant stuff here. And the reason I'm trying to do this is because I can't make a constant that's going to be able to handle the job of a variable and vice versa. They are, in a sense, separate from each other. So what I'm seeing here is that even though we start with one equation and two unknowns, a and b, by factoring, by grouping here, by knowing that the x parts need to make on the left need to make the x parts on the right, and the constants on the left need to make the constants on the right, I can now make some statements such as, well, the x parts on the left have to match the x parts on the right, so I think I can make the statement that says 0 equals a plus b, and therefore a and b are opposites of each other. Similarly, I think I can make the statement 2 is the amount of constant that we should have accrued. And I know that my constant component, if I use the breakdown that I chose, should be negative a plus 4b. This now is two equations with two unknowns, so we can actually solve. So I'm noticing here, this doesn't get me directly anywhere, but this allows me to make a substitution into these guys over here. So I think I can now use this piece of information to rewrite this as 2 equals positive b plus 4b. So it looks like 2 is going to be 5b, and it looks like we have just solved for our first of our two parameters here. It looks like we're going to get b is going to be 2/5. Further, I know that b is going to be the same thing as the opposite of a, and so it must be the case that a here is going to be negative 2/5. And what this is allowing us to conclude then is that 2 over x minus, I'm forgetting my fractions here, x plus 4, x minus 1, 2 over x plus 4 times x minus 1. Apparently, that's the same thing as, we wrote this as a over x plus 4 plus b over x minus 1. So it looks like I can actually write this now as a is negative 2/5. By the way, I'm going to give you a piece of good advice right here. Often in these cases, even though you should hopefully feel a little silly making a mixed fraction, a fraction, a fraction here, I'm going to tell you that's going to be favorable for us here because denominators like x plus 4 are very favorable when we are integrating rational functions. Introducing these constants, if you were to kind of mash this in here and make this like negative 2 over 5x plus 20, which is another good rewritten version of this, you're just going to have to go undo that once you go to do your integration. So I'm going to say here, just don't. Just leave these guys separate as they are right here. Now, what you could certainly go do is you can go redo this addition, get a common denominator, add these guys together and simplify, and you'll find that you're going to get back to our original integrand right here. So the important thing that we just did now is we started with our original, which was our, sorry, I'm forgetting my things here, x squared plus 3x minus 4 is our denominator. I'm going to go ahead and factor the denominator into x plus 4, x minus 1. I did all my side work, a lot of side work. This is like a heavy side work section right here, where most of the work that you do is all the decomposing your fraction. The whole point is that the integration should be easy at the end. So most of the work in 7.4 is all side work. So it looks like we have decomposed this fraction into two fractions, negative 2/5 over x plus 4 plus positive 2/5 over x minus 1. And I'm now just going to write this as two very simple fraction statements, or two simple integral statements. negative 2/5, 1 over x plus 4 dx, plus positive 2/5 integral 1 over x minus 1 dx. I can't give you easier integrals than these right here. This is just directly, you get natural logs from rationals of constants over linears right here. So I think that I'm seeing here a answer of negative 2/5 natural log of x plus 4 plus 2/5 natural log of x minus 1 plus c. I'm good with this being a good final answer right here. But I just want to say, remember that we have log properties and that we can do some simplifying. So this is a section where people often get an answer correct, but then they look it up in the back of the book and they get discouraged because their answer looks wildly different than the back of the book's answer. The book is going to do a lot of simplifying after this right here. So I'm maybe noticing that I want to like get my positive term first and my negative term second and factor out of 2/5. And if we do this, remember that we get this log property here of subtraction outside the log is just as good as division inside the log. So like I bet, so the book actually doesn't do this one. The book just says set it up. So they won't even have an answer back there that looks like this. But if they did, I bet that this is what the book would give as a final answer right there. I am totally cool. If you're all the way done doing your calculus right here and you did it using a smart technique like we just did, I'm super cool with this being a good final last line right here. But again, recognize that you do know some log properties right here that allow us to kind of rearrange some things. This is obviously a tighter, conciser answer right here. So in a sense, maybe this is preferable, but there's certainly nothing directly wrong with our unsimplified line right there. But I'm just pointing this out because you're going to want to see this for comparing your answers to the book answers there. So again, let me just re-highlight what we just did here so we know exactly what just happened. Most of all of my writing is on the right-hand side of the screen because most of the work that we're doing is side work to rewrite our integrand. This is not directly integrable. We could manipulate the bottom to factor it, and if we can factor it, then we can rip it apart into two different factors. We have decomposed our single rational function into partial fractions rather than a whole fraction right here. We get each of the pieces. We typically denote each of our unknown numerators, how much of this fraction do I need, how much of this fraction do I need, with capital letters right here. And we can work to solve for them by factoring by grouping. Our x parts have to, on the left, have to agree with the x parts on the right. Our constant parts on the left have to agree with the constant parts on the right. If we end up with quadratic terms, then the quadratic terms on the left have to match the quadratic terms on the right. This allows us to actually build n equations with n unknowns, even though we initially start always with one equation with n unknowns, which shouldn't work out for us, but by matching coefficients, we can get this, we can solve for some variables here. Once we've solved for this capital A, capital B, and all the other letters we need to solve for, then we now have a decomposition of our original fraction into simplified rational functions. Each of these are easy to integrate. So now we come back and like notice that like literally this was all just me rewriting my work from above. The actual calculus lines right here were nothing, right? The calculus work that happened was simple. It was the algebra that was the complicated algebra here. And we want to know why we care to do this calculus or the algebra that we did. And that's because hopefully you very much recognize these integrals were super easy. The original integral that we started with, we literally don't even have a technique to come at this guy. So we had to decompose it into simpler parts first so that we could then do the calculus second. So very much an algebra section here today. The whole point is we're going to work to fight to get into easy calculus situations. It's the fight that's the hard part getting there. So let's see some more that are associated with this guy. This will be a pretty similar example, this guy right here. Number 13, this is almost number 13. It's not quite number 13. I modified it a little bit. You should notice that the very first thing that happened when I was back here is that the first thing I did today is I felt stupid because I got in a factoring fight with myself in my head, as you're going to do this week because you're going to forget small, tiny algebra things like this. I got in a little factoring fight with myself in my head, and that immediately bothers me because I assume that I'm good at factoring all the time, which is not necessarily a responsible assumption for me to be making. So I want us to really remember that we all are very capable factorers here. So the point is that we learned in the last example is I really want to rip this beast apart. And the way that I get to rip this guy apart is if I can rewrite it in factored form, then rip apart the factors. But what I'm seeing is that this does not look like what we consider a factorable quadratic in algebra land. But what I do know is that anything that's written as, oh, come on, I don't understand. Like I'm clicking on the thing and I'm right, so right. So what we know is that anything that looks like x squared minus y squared can be factored into difference of squares, x minus y, x plus y. Right? What I'm seeing here is that that's not really perfect squares right there, but I can think of this as being like x squared minus root 5 squared, right? A little awkward, but kind of not really. And just get over it because root 5 squared is 5. So root 5 isn't really a perfect square like 9 or 16 or 25, but like, who cares? I know exactly what the square root of 5 is. It's the square root of 5. So I should be able to do it this way. So what I'm thinking to myself is we should be able to do like an x minus root 5 and an x plus root 5 if we want to go ahead and rip this guy apart right here. All right. By the way, you should notice here, if this were a plus sign in here, you'd be doing trig sum. If this was a plus sign, this would match the format that we've seen for some of our trig subs here. But it looks like we can do this with some partial fraction decomposition here instead. So I am going to suggest here, and by the way, I'm going to go ahead and do myself the smart favor here, and I'm not going to write an integral symbol again until I actually plan to do integration. So I'm going to say x squared minus 5. This is all my side work here. I'm going to say to myself x squared minus 5. Well, I know that I can write this as x minus 5, x minus root 5, x plus root 5. And therefore, 1 over x squared minus 5 should be equal to, we should be able to get two linear terms with this again, x minus root 5 and an x plus root 5. Also realize small things, like the fact that I'm choosing a plus right there, it doesn't mean that I know that this is going to be like a positive number right here. If there's a negative, it'll crop up in that parameter. I don't really need to worry about stuff too much like this. I'm also going to, I think I'll make this statement. All right, I'm not going to get ahead of myself. I have some other like general advice statements here and things that you don't need to worry about, but I've got those written down, so we'll get there. So again, I'm going to take this entire thing and I'm going to multiply this whole dang thing now by x squared minus 5. And what I really know that I'm actually multiplying by is this guy right here. There's these factors. So on the left, I just have 1 remaining because I've multiplied by the entire denominator. On the right, the a term cancels the minus factor, but the plus factor survives. On the b term, the plus factor cancels, but the minus factor that I multiplied by survives. I have 1 equation and 2 unknowns, which initially feels like a problem, but what I know is going to happen is that we are going to match coefficients for my x terms and my constants, and that's going to get me all the information that I need. So I'm going to write my work a little bit quicker here, see if you can keep up with this here. My 1 remains on the left. On the right, I am imagining doing my distributing and my recollecting of terms all at once. I can see that my x stuff looks like I have an ax, and I have a bx. And so in total, what x stuff do I have? Well, I have a plus b of it, right? Do we all agree that there's ax's and bx's for a plus b x's here? Similarly, for my constant term here, it looks like I have a root 5 minus b root 5 is my whole constant term that I've got that I'm working with right there. So very similarly, I'm going to go ahead and add for myself this artificial 0 x's right there plus 1 constant. I'm going to lump my terms together here and say no x's. Well, that's got to match my a plus b x's. So again, we're going to get a 0 equals a plus b. These are types of things that are really common to see. It's not just a coincidence that this happened in my first 2 examples. This is a very typical thing to get some of our parameters matching in this way right here. So I know that a is negative b. So this is now going to allow me to make my other statement, or excuse me, I was already able to make my other statement, but I wasn't able to solve for it, right? Our constant term of 1 should match up with our constants of a root 5 minus b root 5. The fact that I know that a and b are opposites of each other allows me to rewrite this, for example, as it looks like negative b is the same as positive a. And it looks like I've found that a is 1 over 2 root 5, and therefore it must be that b is negative 1 over 2 root 5, and we have decomposed our fraction. So it looks like now I've done a bulk of side work. What I now can do is go back and actually do the original integral here. Our original problem was 1 over x squared minus 5 dx. I have now discovered that I can rewrite this in terms of a's and b's using the a's and b's found here. So it looks like what we're going to get is the integral of a, I found to be 1 over 2 root 5. Remember, do yourself this little favor right here, keeping that together. And that was associated with my x minus 5 denominator, plus, looks like b is negative 1 over 2 root 5, x plus root 5, so root 5 dx. Just like with the last one, these are going to be two super easy integrals. I just want to rewrite this in a maybe slightly cleaner form for myself. Pull my constant out front, rewrite it as two integrals. And we're cruising. We got our answer here. Nope, that's a minus. Oh, come on, man. Seriously? Can I not redo that? Okay. Apparently that was all one chunk. Minus 1 over 2 root 5. Integral. Oh, that's not. Okay. Jeez. Not doing an integral. We got our natural log of x plus root 5 plus c. And again, our book might, I would anticipate our book would probably factor out the 1 over 2 root 5, and then natural log minus natural log is going to be division within a natural log. So I am anticipating, I haven't looked, but I would anticipate that this is probably the structure of how your book is reporting this answer in the back. We did have that constant coefficient that was similar between both of them, so I factored it. Natural log of a minus natural log of b is natural log of a divided by b, and that's exactly what I've got right there in our absolute values. So this one's pretty similar to the previous one. Just realize that, like, while I think that people often learn in algebra class, they're like, oh, well, this is sort of like difference of squares, but 5 isn't a perfect square. It's like, yes, it is. 5 is the perfect square of square root of 5, so you can still do this thing right here. And these are things where, like, in your life up until now, it might not have been smart for you to think about factoring in this way, but now it is, because we really, really have a strong desire to rip this guy apart into its constituent pieces, and you literally don't have a way to do that unless you can get something that is like a quadratic into factored form. If you can't get into factored form, then you can't get into your decomposed form, so that has to be there as an intermediary step. So here, really just like kind of get over this right here. If that's something that bothers you, as of today, work on that not bothering you. We should be able to factor these exactly, whether it works out with nice clean integers or not, and then to use those factors as our decomposing denominators here. Add this term. I think this is a helpful thing to write. This helps me remember that I'm trying to group up things according to how much constant is there, how much x is there, how much x squared is there, how much x cubed is there. Later, next semester with me in DiffyQ, you're going to get how much sine of x is there, how much cosine of x is there, how much e to the x is there. And we're just going to give unassigned coefficients like this capital A and capital B, and we're just going to solve for how much there must be so that things work out for us. We're just going to say, we know there should be some parts like this in here. We just don't know how much of A and B to add together. We can just solve for those things based on knowing what we want the result to look like in a different form. So those are two of our, in a sense, simpler examples here. Let's look at some more complicated things here. In example 3, my question here is really just saying, don't do this whole problem here. There's no integral here. Just write out what the decomposition would be with this guy. And this is really, this is just in a sense me stating some rules for you. And so I just want to show you how it would be appropriate to break this guy down. And I want to emphasize to you that your only risk is that you don't break it down enough not that you break it down too much. There is no such thing as over decomposing. There is such a thing as under decomposing here. And I just wrote some of my powers backwards, so that guy's going to look like that. So here's the way that this is going to work. Here what you can see is that this is nicely in factored form. Your first thing you should be saying to yourself right now is, oh nice, starting factored form. That's important to us here. If it was in expanded standard form, then you then have to go work to get into factored form, and that kind of sucks. Here we're already factored. So what's going to happen here that's different than before is that before each of our factors only cropped up one time. We never had a cubed factor or a squared factor. What we'll want to account for here is the possibility that we want to consider a denominator of x, a denominator of x squared, and the denominator of x cubed are all possible chunks that we might want contributing individually to make up this fraction collectively. So here, if I'm going to decompose this guy, what we're going to get is an individual chunk of each of the possible... Oh, man. What am I doing to myself here? I don't understand why I can't write today the same way as I've written in the first 5 weeks of this class. It would be super cool if that was the case. Okay, so we're going to get one copy of x, or we might want to consider a term that actually has the x squared, because x squared is technically one of the factors down here. It might be that the best way for us to think about this, we just can't see it, is this being like x times x squared, and maybe in a sense that's a helpful decomposition here for us. It's unclear, so we include that as a possible term. It also might be thinking about that as all x cubed parts together is what's in our best interest, so we include that. So notice here, since this term was repeated 3 times, we wanted to include all possible combinations of that term cropping up down here. Similarly here, we will include the option of the x plus 3, but also we notice that there also might be some terms down here that are associated with the x plus 3 squared as well. And so an appropriate decomposition setup here would be listing all possible powers of each of the individual factors that appear in our denominator. Since the factor x was repeated 3 times, we included all possible numbers of times that we could have experienced the x, all possible number of times that we could have experienced the x plus 3. In this case here, we're going to have a little bit of a tougher time solving for a, b, c, d, e. Certainly 5 parameters is just going to be more work. It does get to be the case that like if you're doing very complicated one of these on a computer, it's certainly going to be making a matrix of solutions and doing a matrix of linear equations and solving that. It'll be much more efficient for a computer to do that once we have a large number of parameters here. So as far as just writing out this decomposition goes, and yeah, I'm just verifying this example 4D in our textbook, or wait, oh, it's number 4B, not example 4B. Example 4B in our textbook here just suggests each possible count of each of our individual factors. Finally, what we want to consider is that the only reason that, okay, sorry, we're going to look at a list of things and see one other possible outcome. It's sort of our most difficult scenario to handle here, but we'll make some generalizations here before we do that. So, in general, wait, do they all actually land there? Oh, nice. So here's kind of our generalization of how we hope to decompose things. First things first, if you, like me, are a lazy person, then our hope, right, not necessarily our goal, but our hope is that we can factor the denominator into all linear, non-repeated factors. That's what happened in example 1 and in example 2. We factored into linear factors that were not repeated. X plus 4 is a linear function. X minus 1 is a linear function. Neither of them were repeated. There was no squareds or cubes. Down here, x plus root 5 is a linear function. X minus root 5 is a linear function. Neither of them were repeated. So unique linear factors is by far our best case scenario here as far as simplicity for ourselves. In this case, we just give a constant parameter, just the a, just the b, up in each of those numerators up there, and we're good. It might be the case that we get repeated factors in the denominator, like we just got in example 3, repeated factors in the denominator. In this case, you need to include a fractional term, a fraction, one of our partial fractions, associated with each possible grouping of them. There could have been 1x, there could have been 2x's, could have been 3x's. So therefore, if you get like an x cubed as a factor in a decompose it in a denominator as a factor and not a sum, right? If you had like x cubed plus 5x plus 9, x cubed is a term, not a factor. It needs to be x cubed being included multiplicatively amongst other multiplicative factors here. In that case, we then get each count of each factors gets its own partial fraction here with a constant numerator term. Finally, our biggest bugger here is going to be what happens if you get stuff that's just really not decomposable into those terms like that. Well, in that case, we're always going to get a numerator term that is of degree 1 lower than the denominator term that we've experienced. So in this case here, if we ended up with a sort of an irreducible quadratic factor, then we could give it a linear factor that is on top, or a linear how much of it's on top, to help us with our decomposition there, the ax plus b. Now, what sometimes happens to me is I sometimes forget these rules in my head. Sometimes if I'm doing a problem like this, it's totally happened to me where I'm like, wait, I remember that there's something where maybe it needs to be like an extra part in there or something like that. So here's what might be the case. Maybe it's the case that you're sort of forgetting this rule and then you're getting concerned and you're like, wait a minute, what do I really need for the numerator of this guy over here? Maybe you get nervous and you go ahead and you do this, and I'm going to put this in quotes here, wrong. And you think to yourself, but isn't that like a quadratic down there? Isn't that maybe going to need like actually like a linear term up top? Maybe something like this. Maybe this is actually what that needs to be. Here's the deal. You don't need to go fight yourself and guess through all these things. If you set it up like this, what we're thinking is if this is truly the appropriate decomposition, then this EX term isn't really necessary. It should just be a constant term that's necessary. And so in this case, really E looks like actually F right here. If it's the case that you didn't need to include an X component up in the numerator, that's fine. When you go to the process of solving for all of your parameters, you'll just get that E is 0. And all that you'll have left is the constant term F, which will match up with what we were originally calling E right there, and you'll be in the exact same scenario. So that's what I'm saying. You can't over decompose these. If you can include more parameters that are necessary, then you're going to just solve for information that says, oh, there's none of that part. Oh, that E is just 0. You have no X component associated with that numerator up there. So what I would urge you guys to do is to maybe on some of these simpler ones, like maybe when you're doing like this example right here, even though, and I mean, let's even go to the actual like really easy one right here. Do one of these where you choose your decomposition to instead be something like, maybe pick this to be like ax plus b and see what happens. What you should see here is that the blue or the red b is the same as the black a. So in this case, I'm anticipating that when you do this process, you're just going to get a equals 0. And that's going to tell you there's none of that part. And then you'll just get the constant parts that are left over. I think it's worth it to do that once to see that that's going to happen, because that what lets you know that you don't have to stop and like really grind your gears on this and be like, oh, I don't know, is that an ax plus b or is that just an a? Just include the extra terms. If it's extra, you'll solve for it to have been extra, meaning it will just pan out to be equal to 0, and then you don't have to think about it. And so you're good there. So realize with these ones, the only concern is that you under decompose. Over decomposing is not a thing. It's going to make a little bit more work for you, but any extra parts that you introduce will just go to 0 in your natural solving, and then they just won't be represented in the final solution because they shouldn't be, and you'll know that because you got 0 for that contribution for that parameter. So the point here is, in my last bullet point, if you aren't sure if you need to include a parameter like some a or some ax or some bx squared, you can just include it. And if it didn't actually need to be there in the first place, then you'll find that 0 would have been the coefficient associated with it right there. So you can't overdo it. You can really only underdo it on these ones. So don't underdo it. If you're ever unsure, throw in an extra term. You'll get extra stuff. So let's look at another example here. So the next two examples that we're going to do, I'm going to tell you right now, we're going to do only example 4 and example 5 that I've got right here. And in fact, let me actually, for the first time ever, bring my two examples closer together instead of further apart to point out to you how this is going to go. I like to think about people's natural reactions. Gosh, I got to say to you guys, out of the million reasons why I wish we were in person this semester, I like to see what people's faces look like when I write a problem up on the board to see if people are just like, or it just looks like everybody just threw up in their mouth collectively at the same time kind of thing. And really what I like to do is write sort of two problems up side by side and just have people do things like say like, which of these looks worse to you? And what I should at least think here is I am anticipating that each of these probably looks at least like approximately equally crappy for you to manage right here. And what I am going to emphasize to you is that example 5 down there is basically going to be a piece of cake. Example 4 up here is the one where we've got to be a little bit more careful. I think example 4 is the hardest one that we're going to do today, and it's going to be the one that we're going to do it two different ways because it's not clear to me what is the best way to do it. So example 4 is very much going to get us back into our theme of like, I don't know, guess something and go until you can't go any further and see where you get. Example 5, we're going to just kind of nail it because our first guess is going to make a lot of sense for ourselves here. So these are the two we're going to do today, but I'm going to do example 4 twice because I think we're going to get a little bit hung up. Example 5 is going to turn out to be pretty easy, even though it's got those trig terms stuck in it here. So here we are. I think this is our tough one today. Example 4 is number 40 from the book. And what do we see? Well, I go down my checklist here. And by the way, when I talk about my checklist, I hope that you have seen that section 7.5 in your textbook is literally, what should my checklist be for doing integration? So like when I'm saying I'm doing this checklist in my head, I am thinking about like a flow chart of like, what should I try first? What should I try second? What do I hope is going to happen? What would be the nicest thing for me to happen in each case? My first hope always is, can I just do this? Do I just literally just know the answer to this problem? It feels ridiculous to say that out loud, but like, more often than not, there's some things where it's like, oh, I just do one tiny algebra step and I'm good. I don't see that here. I really don't see a one tiny algebra step that's going to take me home on this guy right here. And I don't. One thing I'm thinking is it could be maybe. And by the way, this is really going to be like a let's just try stuff problem here. So I'm going to just write down some stuff I might try. What would a conjugate look like if I multiplied by a conjugate here? X minus x plus 2. My conjugate here would be multiplying by x plus root x plus 2. And let's see what we get if we do this guy here. X plus root x plus 2. If I do this, then I am going to get x plus root x plus 2 on top, which is kind of bad. But on the denominator, I should be getting x squared minus x plus 2. And so I guess I could rewrite this as like this guy. Technically, I don't know. I don't know if I've helped myself too much right here. The thing that I'm seeing is it looks like this is not a factorable denominator down here directly, which is a bummer. We could go to the quadratic formula, get our roots, rewrite it in factored form based on those roots. That would be pretty gross. I also think I'm going to really struggle with this one. I think I could actually probably do just this part by partial fraction decomposition alone. This one with that root in there, that's giving me some issues right there. I would have to really be able to deal with that x plus 2, and it's not clear to me how I would do that right there. So I'm going to go ahead and say, as I'm planning to say in many situations here, it doesn't look like that's going to get it for me, because I'd have to be able to manage both those cases, and that's going to get pretty tough right there. Another thing I could think to myself is like we could do some like U sub. We could do parts. We could do a trig sub. Like I'm hoping that the lesson that you learned from the trig sub section is I hope we don't do trig sub. But again, this is a tough sell for me to see some trig stuff, partly because this could be like an x squared minus something else squared, but then I don't know. That doesn't look great for me here. And besides, I'm seeing x components in both pieces. None of our trig stuff had x stuff and x stuff in both the parts right there. So that's sort of out for me as well right here. So it feels to me like there's got to be some u sub to make, but the u sub thing that I don't see is I don't see that we have the derivative of something, or I don't see like a part and its derivative in here either. But again, I'm sitting here just kind of spinning my wheels. I'm very much still in the process of like, I don't know, try something. And you really need to be in that mindset for lots of integration. You can't be afraid to just write down and attempt at something here. So if I were going to do u sub, like what would I even pick? And And the answer here is I literally don't know. And I'm going to go ahead and tell you now that I'm obviously trying to phrase this like, I don't know what I'm doing. We're exploring here. I'm going to do two different U subs here today, and we're going to kind of just feel them out as to which one worked out better for us here. I think that one not crazy U sub idea here, and I'm going to call this U sub number one, and I'm going to put this in a red box because we are going to do, this is going to take us a little bit of work to do these, and I want to make sure that we see attempt number one and attempt number two and how they both went for us. So the first thing I think I want to try here is say, you know what, x plus 2 underneath this square root, it's really screwing me up. Let's make it not be like that anymore. All right. So if I do this kind of action right here, then I'm at least getting things that look like x minus root u. That at least makes me feel a little bit better about the u parts right here. So I still need to get dx replaced. I still need to get x replaced. So I'm seeing a couple things. One, I'm seeing that du is equal to dx easily. That's really nice. The other thing that I'm seeing here is that we can subtract 2 from both sides, and then I'm going to get u minus 2 is the same thing as x. So if I do this, is this helping me at all? It looks like here I should be getting 1 over x is now u minus 2 minus root u du. And did this help me? That's like always my question. I'm like, okay, I attempted something. I tried to do an adjustment here. Was that a useful and practical thing for me to do? Or is that not actually the case here? It's really funny. And I'm laughing right now because I'm looking at my notes and I'm realizing in my notes I got like stuck on this method as well because this didn't quite work out for me. As it's not right here. I'm like, that's not the wrong thing I got in my notes before, or the not working thing I got in my notes before. This is just a different version of stuff that doesn't work for me. And again, my issue right now is like, how would I factor this guy? Like, I don't really have a way that this factors at all. I need a factored denominator. I'm not quite seeing that one here, so it doesn't look like this is working out for me here. I don't know how I'd get factored here. So again, it's not like I know what I'm doing yet, but I really just kind of feel like that's also like not a route that I want to be going here. So let's go ahead and try another. And again, I hope that you really are getting on with the fact that like I'm not just making this up. A lot of integration is developing intuition through significant amount of experience. And the way that you develop that intuition is by having tried everything and trying to develop this like subtle intuition. It's like, why didn't that work? Why, how should I have known that that wasn't going to be good for me here? And it's hard to tell these things. Here, kind of what I saw was that I still have addition and subtraction of a sort of a linear term and a root term. And that seems to be what's really bothering me here. So maybe it wasn't so much that this x plus 2 under the root is my issue. Maybe the issue for me is really just the entire square root down there. Maybe that's the thing that kind of sucks for me. So how about I do this instead? How about I do all of this? I'm going to just swap out the whole thing, the whole square root term down there for you. Now, immediately, seeing what du is going to be seems a little bit less obvious to me, but I do think I can do my little algebra move right here and at least do my like u squared equals x plus 2. And this allows me to make a statement like, it looks like x, I can subtract 2 from both sides. X is going to be u squared minus 2. And I think this allows me much more easily to make a statement like dx equals 2u du. All right? So again, I really don't know if any of what I'm writing right now is helpful. I'm trying some stuff. I'm creating components that allow me to do some rewriting so I can say, was that good? Does this help? Does this help? Does this help? So where are we at here? We had a 1 over, I'm forgetting 1 over x minus root x plus 2. And based on the substitution that we're looking to make right here, let's swap all of our pieces out, right? According to our substitution, x is now u squared minus 2. That's x. Minus, what are we subtracting off? Well, root x plus 2 is really just u. All right. What do we have on the end over here? Well, we have dx, and dx is going to get replaced with 2u du. Right. There's my substitutions, my 3 substitutions. They're all indicated with parentheses, right? So again, I thought about a conjugate for a second because I saw addition or subtraction with a fraction I didn't like. That didn't seem to be going anywhere. I tried a gentle u sub. It didn't seem to take me anywhere. I'm now trying what I would think of as a more aggressive u sub. I'm taking out a bigger chunk of my function here. It's still not clear to me if this is helpful, but like now we want to rewrite and see where we're at. Okay, excuse me. So my 2, constant multiple 2, I'm going to pull it out front. This u, I'm really thinking of as being part of my numerator up here. So u in the numerator. In the denominator, it looks like I have a u squared minus u minus 2 du. And now we're saying to ourselves, did this even help me? And the answer I now think is maybe. Remember kind of what our goal here is. Standard form of the denominator sucks for us. We want factored form in the denominator, and it looks now like I can actually finally pull that off. All right. So we now actually have a factored denominator in terms of u. Also, notice, interestingly, in the first 2 examples that we did, we had a constant up here in the numerator. We now have a variable, so we're going to expect to see some slightly different things out of our partial fraction decomposition. So what I'm thinking now is I feel pretty good that we're going to be able to be taken home on this one. I feel pretty good that u sub choice number 2 is going to be good for us. So let's go ahead and start our partial fraction decomposition. I'm going to move way up since I know that this always takes some room. Oop, not a B, a P. Hey, thank you for letting me erase just one thing. How generous of you. Partial fraction decomposition. And it looks like what we want to say is u over u minus 2, u plus 1. Since we have individual denominators with the power of 1, right? We're in factored form. Each of the terms is linear, and we just have this, and they're only represented once each. We should still just get to do a constant of a and a constant of b for our 2 numerators, and this will go with our u minus 2 partial fraction. This will go with our u plus 1 partial fraction. We're going to multiply, and I'm going to show less work on this one and just say it. We're going to multiply this entire thing always by the denominator on this left-hand side. That's always going to just leave me with the numerator on the left-hand side. We can see that when we multiplied by u minus 2 times u plus 1, the u minus 2 canceled in the first term, leaving us with an a times u plus 1. This is almost like a sort of like a false version of like cross canceling here, like cross multiplication or something like that. It's not really that, if you know what I'm talking about, but like it feels to me like that, right? Like we get the opposite terms linked with each of these things because the term it already had canceled away. So I'm getting here a plus b times u minus 2. It's the opposite term there. And again, now I want to find out what my a and my b are going to be. You should notice in this case now, this is more like 1u plus 0 equals, well, how much u stuff do I have over here? I have a u's and I have b u's for a total of a plus b u's. For my constant stuff, I have 1a minus 2b. So this allows me to do my solve by grouping here. I know that my u stuff needs to match my u stuff. I know that my constant stuff is going to match my constant stuff. I'm going to start solving the equation that seems most helpful for me to start solving. Hopefully you've got your algebra experience here. A equals 2b. That's going to tell me that 1 equals 2b plus b. At 3b, so I'm getting 1/3 for b. If b is 1/3, then this is going to tell me 1 equals a plus b, tells me that a is 2/3. So I have done my partial fraction decomposition here. I think I'm ready now to, in a sense, wrap up this problem. We had to do a u sub first. Turns out we picked the wrong u sub, but that's just the way she goes sometimes. Sometimes she goes, sometimes she doesn't go. That time she didn't go. It's the way she goes. This time, the second one, we picked a second choice for u sub that seemed to actually be more helpful for us. It got us into a quadratic denominator that we were able to factor. Since it was a factorable denominator, we got into factored form and we performed partial fraction decomposition. We decomposed. I now have my decomposition rule. It looks like this should be now 2 integral of. Notice that the integrand u over u minus 2 times u plus 1 is exactly equal to this sum right here. This 2 had nothing to do with my partial fraction decomposition. It's been along for the ride on the outside this whole time. So what I'm seeing here is 2/3 is my first power. So I'm going to get 2/3 over u minus 2 plus 1/3 over u plus 1 du. And here, man, I can even squeeze in my answer, right? Tony, could squeeze in my answer, but I do not want to encourage you to squeeze in that answer. So let me just write this here as our final answer then. It looks like I'm getting 2 times. And by the way, I'm maybe even hoping again, like I skipped a bunch of steps over there when I was doing my partial fraction decomposition. I'm going to skip a calculus line right here also. Hopefully we can see this as 2/3 ln u minus 2 plus 1/3 ln u plus 1. I'll go ahead and stick my plus c on that. By the way, other little technicalities, that plus c, technically you would be correct if you included it in here or not. It's just a constant. When we go to solve for it, it will end up being the value it needs to be. Locate it sort of where you want as long as it's not like combined with some variable terms and you're good to go. This is another one where I'm going to go ahead and beat this thing with an algebra stick as much as I can just because I don't know what the back of the book would say for this answer here, and I want you guys to maybe anticipate having to manipulate your answers to get them to agree. Here what I'm seeing is it looks like I really have maybe more like a, all right, I'm going to leave that 2 there. Here's kind of how I'm thinking of this. Okay, I guess I got to back up a little bit right there. Oh, of course, I'll just back up the whole thing, no problem. So let's write this as 4/3 ln u minus 2. Oh my gosh, I tried to stop when I was in U land. See, this is why I need to be in person here. I make some small mistakes. I need somebody catching me here. We're not in U land, we're in X land. We'd better be getting back in terms of our original variable here. But there's no reason to get back in terms of our grosser stuff while we could be in our nicer stuff here. So maybe I am thinking here. This looks to me like, all right, I'm going to say that maybe that wasn't my smartest rewriting here. I'm going to do some factoring out first rather than multiplying through. I think that I want to factor out this 1/3. So I'm going to think of this as 2/3 2 natural log of u minus 2 plus natural log of u plus 1 plus c. I'm going to go ahead and move this 2 in as a power. Wait, was that a plus between them? Okay, that was a plus between them. We did get positive for A and B. I was thinking that this was a negative. That was subtraction between those two right there. And so in that case, so I'm going to drop my absolute values here. They technically belong there. It's just, I think that's kind of distracting from the big idea that's happening right here. I took my 2 here and expressed it as a power on u minus 2. And addition between natural logs results in multiplication within the natural log here. So this might be a simplified version for writing this. And then finally remember that we originally started this whole dang thing with, I believe, this substitution. Wasn't it root x plus 1? Root x plus 2 is our substitution. And so I think I'd state my final answer for this guy probably as, and honestly notice like this 2/3 power could even go on this whole thing right here. If we wanted to right here. So maybe 2/3 natural log of, and we're getting here, root x plus 2 minus 2 squared times root x plus 2 plus 1 plus C for that good final answer right there. I'm assuming our back of the book probably gives it in that format right there, a solutions manual that's out there. Right. So remember to get back into Xland. I tried to finish that problem in U, which was inappropriate of me. So we fought our way back into X. But again, I want to really, like, literally on your whole screen right now, all you can see is me doing algebra. The algebra was what was happening there. On this whole screen right now, there is essentially one calculus step that happened. Actually, no, there's no calculus that happened on this whole screen. The only calculus step that happened was going from this line to this line. The only calculus was this one step that happened right there. Okay, that's a bit of a lie. We did our U sub up top also. That was important for this guy. There's a little bit of calculus that happened. But again, just emphasizing, like, this is really algebraic. This is really saying you need to be competent in your manipulations so that you can fight integrands into being integrable integrands rather than non-integrable integrands right here, as that one currently is formatted as such. So we want to be getting into polynomial settings typically, not necessarily having to be polynomial settings, but we want to be in settings where we can factor our denominator, because factor denominators can be decomposed by partial fraction decomposition. And if we can decompose them, then the integrals are easy. Integral of 1 over x is ln x. Right, there's not much that's really happening right there calculus-wise. It's pretty simple integrals. So very much an algebra section here as opposed to a calculus section. So let's take a look at one more example. As promised, this one's actually not going to be that bad. I don't even think I need any more room than this one. I always am wrong when I say that, but that's okay. Let's start this guy right here, and I'll be able to shift it all down if I need to. You know what? No. Why am I dumb like that? Why do you guys let me get away with those statements right there? Be smart, Tony. You're a smart person, allegedly. Okay. Give myself the room I need here. So what we should certainly be seeing here in example 5 is that it's just not obvious what to do. When I say that, what I mean is, no, this does not look directly integrable to me. 2, even if I made a U sub, it's not obvious kind of where I'd go directly from that U sub. I don't see necessarily an integration by parts, because sine squared plus sine is going to be a really crappy part regardless of we pick that for U or for dv. As far as trig integration goes, I could maybe try and do like some factoring with this. Like, I don't think it's crazy for us to think about things like cosine of x over like sine x times sine x plus 1. But like, when do we get sine x plus 1 not squared and that be useful? Like, that seems suspicious to me as like not what we want. Other things I could think, this is right, but like, is it helpful is sort of what the question mark is indicating. Other things I could think. Sine squared. I know how to rewrite sine squared, so maybe one of the things I want to rewrite for myself is like a 1 minus cosine squared of x plus sine x or something like that down here in the denominator. Does that seem helpful to me? I don't know if that's helpful, because now I've got 2 different trig expressions down here. I'd say the one nice thing that I'm seeing about this problem is that this problem at least does look quadratic in sign down here, right? It's something squared plus something, and both in terms of x right there. So I just feel like both of those don't seem super helpful for me as sort of like trig attempts to make to alter things right here. Integration by parts doesn't seem great because that denominator as a part looks like it would suck. So again, this leads me to be like, I don't know, is there a substitution I could do? And I might think to myself, sure, let's try something here. Could I make a U substitution here? We are smart enough to stop and think about this one. I am hoping that you recognize that some good U sub choices here are either U being sine or U being cosine. If I were to pick U to be cosine, I'd get du is negative sine x dx. But you should notice that the sine components are in the denominator and the dx is in the numerator. So I don't think I want to go that way. In this case, therefore, I think it would be better to pick sine x as the u, because then we're going to get du is cos x dx, and I do have cos x dx as part of my integrand here. So it looks like we can do a u sub here, and again, I want to non-stop emphasize this. It is still not clear to me that what I'm doing is useful. I'm just trying some stuff. This is a stab in the dark. We are just hoping that the room feels slightly more brightly lit than the last time that you stepped into it every time. It shouldn't be just stabs in the dark anymore, right? As I go to make my substitution now, I'm seeing that we're getting cos x dx just became du. In the denominator, sine squared, well, that's u squared plus u. Well, that's nice and easy right there. The reason why this is excellent to me is because this just panned out to be a quadratic in the denominator, and it's a factorable quadratic, in fact. And so this looks like something I can decompose. And so now let's go ahead and take this guy, do our partial fraction decomposition. Let's see how quickly I can do this one. U times u plus 1. I'm going to give it my, again, it's still unique linear factors in the denominator down there. I'm going to multiply by the denominator of the left. It should give me u plus 1 as my parts for A, and u is my parts for B. I now want to group them all up. I'm going to have 0 u's plus 1 on the left. On the right, I'm going to have a plus b u's, and I'm going to have a as my constant term. Therefore, 0 should be a plus b. 1 should be a. That one's pretty nice and easy right there. Since a is 1, that's going to tell me that b must be negative 1, because we have a and b add to 0. And so it looks like I now know my decomposition components right here. I've got the constant coefficients associated with my decomposition. So it looks like I should be able to rewrite this integral then as we've got a over u, that's going to be 1 over u. Looks like b is negative 1, so I'm just going to write this as minus 1 over u plus 1 du. I've figured out my decomposition here. This should be giving me a pretty nice and easy natural log of u minus natural log of u plus 1 plus c. I'm going to go ahead and do my little natural log simplification here of u over u plus 1 plus c. And because I'm being responsible, I'm going to remember that I originally defined u to be sine of x, so we should get back in terms of sine. And so this is going to give me now natural log of sine of x over sine of x plus 1 plus c. So I hope that you recognize that this was actually a pretty reasonable one to do right here. We had to do a u sub to get started to get us into a situation in which we could do partial fraction decomposition, but it was a really easy u sub to do. It did set us up really nicely for the partial fraction decomposition to be done. So I do want to point out that there are some other ones in the textbook. I'm seeing things like, and I'm not going to do this one right now, I think that we're good with this, but are very similar setup for this guy. The other one that I was debating was that I'll just write this one out and not do it here. But I think another good one here is in number 47. The book sets up e to the 2x over e to the 2x plus 3 e to the x plus 2 dx. And again, in a sense, like hopefully this looks terrible and crappy to you to deal with, but on the other hand, hopefully it looks obvious to you that we want to get that e to the x stuff out of there. And so I'm seeing this as u equals e to the x. Therefore, du equals e to the x dx. And it looks like then we should have the integral of, notice here that this is e to the x times e to the x up top. Down here, this is really just going to be u squared plus 3u plus 2. And the reason I wrote the numerator this way is because the e to the x dx, that's our du. That's going to be a u. So it looks like this one would just be u over u plus 1, u plus 2, du. Right? Not too bad to set up this guy with our u substitution there if we see those guys. So exponentials and trig functions look like they are good candidates for this. And by the way, I do want to just say, like, what you will see when you go to take differential equations with me next semester, which by the way is going to be like the awesomest ultimate culmination, or even Calc 3, honestly, is that like all of these will come up. We're doing all of these this semester because we will do an application next semester where we're going to get terms that absolutely require partial fraction decomposition. We're going to get things that we want to integrate that are going to look like this, and this is exactly how we're going to manage them. You will laugh out loud when you realize when you go take DiffyQ with me next semester that like in the first 4 weeks of the class, we will have come up on an instance in which we require literally one of every single one of the techniques that we've covered in all of chapter 5 and all of chapter 7 in this class. We're not just doing things because they're technically possible. These are all the things that are directly required to solve most differential equations, which are really explaining like every physics scenario that there exists, and then lots of other topics as well, biology problems, mixture problems, all sorts of different stuff that are out there. So these really are all going to crop up. Like I'm gonna smile my big stupid smile at you guys next semester and be like, remember doing this in week 6 last year? And you guys are gonna be like, oh crap. And then you're going to go look it up because you're going to have slightly forgot, but you're going to remember enough that you can do it here. So expect to see stuff that looks pretty much exactly like these. And so expect for me to ask you questions that look pretty much exactly like these. Use U sub to make things look simpler. Use partial fraction decompositions to actually make the integration possible with some simple rational functions here. So these are the examples I wanted to show you guys today. It is true that I did not specifically do an example where we decompose something into a numerator that requires, for example, like an ax plus b term, as I said, is possible to do here. I would say to you, you should certainly go look at some of the examples that you see in the book. I would recommend to you, if you're still sitting here watching this, go ahead and look at example 8 in the book. And they lay out a good example. As you might imagine, those ones just get gnarly. I mean, some of these partial fraction decomposition problems ultimately end up dealing with you solving for like 5 different parameters. And it's hard in a sense, but it's also algebra, which makes it really hard for me to call that hard. It might take a lot of work, but is it really difficult? If you could have done it at 2 a.m. with your both hands tied behind your back, then maybe not. So certainly go look at some of these examples, but I don't think it really adds on too much for you to see those in a sense, because all it's doing is adding to the algebra component, and I am heartily convinced that you are all algebra competent, and if you're not, that you will discover that through this section here, and you will get there. So those are your partial fraction decomposition problems I want to show you. Let me just speak really quickly to the stuff above my head right here. Tomorrow's lecture, we're going to do 7.5. 7.5 is the only section of the entire textbook that says, all right, we feel bad. This stuff has been really hard. Let's talk about it all together. Never is the book so nice as to do stuff like that. So 7.5 is your gift section that says, let's really like put all this stuff together and see all these in relation to one another. So it's really like a strategizing section. There's not really new calculus that happens there. It's really just saying, think about every technique that you've ever seen for integration and start to really think about how to organizedly plan for knowing what technique you're going to use. 7.5 will be the last thing that we'll cover before we take our test. And, so what that means is next week in class, I'm still going to cover one section, I think still just one section. So I'm going to do like 1 day of video lecture content, but I'm only going to, in a sense, cover half as much content next week, because one of the things that you'll do next week is take a test. It is my soft plan for next week. This is not my formal official test dates, times, and plans. But what I'm thinking I would like to do is to do regular, make a video on Monday. Normally I would make a video on Tuesday, but I won't because I'm only covering half as much content next week. It is my soft plan to have your test be available to you on Wednesday at noon, and that the test will be due to me in Canvas by Friday at noon, giving everybody 48 hours, 2 evenings, 2 mornings. So I do want it kind of done in a relatively narrow window of time, but I also don't want you to feel like you're rushing to do this like it's an in-class test. I don't want to ask crazy hard questions, but I want to ask questions that might make this take longer than like an hour and a half from beginning to end for this. Like I'm going to put some on there that obviously I intend you to have to like struggle with a little bit, but I'm not looking to crush you in some way that you like need 48 hours to take this test or anything like that. So I'm going to strongly encourage all of you to, even if you have no plans to do anything with the test on the day that I put it out, like if it comes out Wednesday at noon, even if you're not really planning on doing the test till Thursday, you should really read the whole test when I first put it out so that you can make a solid assessment of how much time you think that you're going to need to handle the tasks on the test. The last thing I'll say is I am going to cover section 7.6 on Monday next week. That will not be part of the test. Our test is going to cover up through section 7.5, which I will cover tomorrow on Tuesday. That will be the end of the content associated with the test material. 7.6 I will cover on Monday of next week, but none of that 7.6 material will actually be present on the test that you take that week. That'll slide on into our next unit out there. And honestly, the second half of chapter 7 kind of gets away from our like pure integration technique stuff anyway, so it's a good place for us to make our split right here. So I'm going to wrap it up here for today. We're going to get integration technique strategy tomorrow's video. We're going to take a test next week, so we'll only cover half as much content. That content will just be the next section of chapter 7, but we'll only cover half as much stuff because I want you guys to spend 2 days focusing just on taking a test next week. So that's where we're at. As usual, hit me up with questions. I'm going to post your, if you read in the weekly guide, which I unbelievably made on Saturday, didn't post it on Sunday, published it this morning because I'm dumb. But if you'll read in the weekly guide, I am going to post a mom homework this week. I am not going to collect a by hand homework from you guys this week, but I am going to, in a sense, give you what I feel like is test review. I'm going to give you guys a bunch of problems from the section 7.5 that I think you should work on your own. And in a sense, you should expect for maybe there to even be some test questions that are basically meant to mimic the ones that I'm asking you to do in 7.5. So this is sort of like really do this uncollected homework from section 7.5 because I'm anticipating it directly providing you help on the test that you'll take next week. So I'll wrap it up here. Happy week 6. I will see you guys tomorrow for some 7.5 video. Test next week. See you guys.